Good day, students. In this clip, we're going to be deriving the Moirvre's theorem, or powers of complex numbers theorem. So to make this derivation, we're going to be deriving it using deductive reasoning, using the product formula for complex numbers in polar form as a basis for our construction. Okay, so let's review what the product formula for the product of complex numbers is. So we have two complex numbers, z1 times z2, and you want to multiply them. Let's say we have the first one, r1 times cosine theta 1 plus I sine theta 1. This is the first complex number. And you want to multiply it with another complex number, r2 times cosine theta 2 plus I sine theta 2. What does the product formula for complex numbers in polar form tell us? Well, it tells us that all you do is you multiply the radii r1 times r2, and you add the angles. Okay, so times cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. Okay, so there you have it. All right, now with this formula in mind, let's go ahead and make our derivation. We're going to do this by deductive reasoning. We're going to take a look at three cases and see if we can form a general case for any n power, and that will result in the Moirvre's theorem. Okay, so we're going to start by taking a look at n equals 1. So for n equals 1, we're going to be raising a complex number, r, um, r cosine theta plus I sine theta. We're going to be raising this to the first power. Okay, so if we raise this to the first power, what does this mean? We have exactly one copy of this, so it equals r cosine theta plus I sine theta. Okay, all right, so how can we express this to see the effect that n equals 1 has on this result? Well, we can write it in this format: r to the first power times cosine 1 times theta, 1 theta, let's change the color of that, 1 theta uh, plus I sine 1 theta 2, okay, 1 theta. All right, so there we have it, let's put a bracket there. This is the case we have for n equals 1. You see where the ones show up. Okay, now let's try the next case. How about we have n equals 2? N equals 2, we're going to be raising the same complex number, r cosine theta plus I sine theta. We're going to be raising it to the second power. Okay, so what does this mean? It means that we're going to be multiplying this number by itself. Okay, so that equals, it's going to be r times cosine theta plus I sine theta multiplied by itself, right? Multiplied by r times cosine theta plus I sine theta. Okay, so how do we find the product of these two complex numbers, which are identical? We're going to use this formula right here that we just reviewed. When you're multiplying two complex numbers in polar form, you multiply the radii and you add the angles. Okay, so we're going to do the same process here. So that's going to give us r times cosine. This is the product of the radii, r times cosine. Let's rewrite that. Um, r times r times bracket cosine theta. We add in the same angle twice. Theta plus I sine theta plus theta. Okay, and then parentheses, then parentheses. Okay, so what does this simplify into? It simplifies into r times r is r squared, and then times cosine 2 theta plus I sine 2 theta also. Okay, you see a pattern emerging out of this? You see how uh, the 1, n equals 1 showed up in the final result. Note how the n equals 2 shows up in the final result. Well, let's consider one more case, and then let's see if we can make a generalization by deductive reasoning based on the patterns that we're seeing. Okay, so how about we have a situation where n equals 3. For n equals 3, we're going to have r times cosine theta plus I sine theta raised to the third power. Okay, what does this mean? It means we have to multiply this by itself 3 times. Okay, so we have r cosine theta plus I sine theta times r cosine theta plus I sine theta, uh, third copy, times r cosine theta plus I sine theta. Okay, now how do we simplify this? We're going to use the same product formula that we just talked about earlier. So if we do that, that's going to give us um, r times r. You multiply the 3 radii times cosine theta plus theta plus theta plus I sine theta plus theta plus theta. Okay? And what does that simplify into? We're going to have r to the third times cosine 3 theta plus I sine 3 theta also. Okay? 3 theta. Now, you see a pattern emerging. Notice that whatever the power is, that becomes the power of the r, and that is also the coefficient of theta in the final result. In 2, exactly the same thing happened when you raise it to the second power. That became the power of the radius, and then it became the coefficient of the angles. Okay, so when you're raising a complex number in polar form to a certain power, that power gets the radius get raised to that power, and that power is also multiplied by the angle. Okay, so let's form a generalization here. What is for n equals n? What is it going to look like? Well, we're going to have r cosine theta plus I sine theta raised to the nth power. All right? So looking at a pattern, what we're going to have here is this n is going to be the power of r, and then we're going to multiply the angles by that same value. So it's going to become r to the nth power. Just as the 3 showed up as a power here, the n shows up as a power of r, and then it also becomes the multiple of the angle. So cosine uh, n theta plus I sine n theta. Okay, consistent with all the patterns that we saw. And guess what? This right here is the Moirvre's theorem. Okay, this is the Moirvre's theorem for finding the powers of complex numbers in polar form. All right. Okay, so let's write this down. Moirvre's theorem. Okay, now how about we apply this theorem to an example? Okay. All right, let's take a look. Consider an example. Example 1. All right, so we're going to expand, for example 1, expand the complex number in polar form 3 cosine pi over 3 plus I sine pi over 3 raised to the third power. Okay? Expressing your answer uh, in polar and rectangular forms. In polar and rectangular forms. Okay? All right, so let's go ahead and do it. So if we have 3 uh, cosine pi over 3 plus I sine pi over 3 raised to the third power. If we look at the Moirvre's theorem, what the Moirvre's theorem tells us to do is we raise the radius to the power and multiply the power by the angles. Okay, so um, we're going to have 3 to the third. That's like r to the n. 3 to the third times cosine of pi over 3 multiplied by the power, which is 3, plus I sine pi over 3 multiplied by the power, which is 3. Okay? Close that and close the bracket. Now, let's see. We're going to have 3 to the third is 27. Now this 3 and this 3 divides out, so we have times cosine pi plus I sine, the same story happens here, these divide out, sine pi. Okay? So guess what? This is our answer in polar form. Result in polar form. Okay? Well, we also have to express this in rectangular form also. So the question is pi a common angle? Absolutely, it is. It is 180 degrees. So in rectangular form, we're just going to evaluate what this is. So what is 27 times cosine pi plus I sine pi? Okay, so evaluating cosine pi and sine pi using our table of common trig angles. Cosine pi is -1 and sine pi is 0. Okay, so let's simplify that further. We have 27 times -1 plus 0 pi. If we distribute the 27 to the real and imaginary parts of this complex number in the parentheses, that's going to yield -27, and that's the final result. All right, so this is the result in rectangular form. All right, so that's that. Well, thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel by clicking here. And you can like the video if you liked it. You just click like down here. And please post a comment to let me know what you think about this presentation. More clips coming from MacroChef.com. Thanks again, and have a wonderful day.